Okay, so this is the second part of this lecture, and we start with introducing the first very fundamental information theoretic quantity called entropy. So the entropy of a random variable x, denoted as you can see here, h of x, where x is a discrete random variable with a given PMF p sub x, is defined as the expectation of minus logarithm of p of x calculated in the random argument x. So let's parse this expression. So here we have learned before what the expectation of a function of a random variable is, right? If you remember, is sum over all values of the alphabet in which the random variable takes on values of the product p sub x calculated at the argument small x times the value of the function at small x. Now here, what is the function in this expression? The function is g of argument is minus logarithm of p sub x argument. Okay? So that's our function. Remember, the subscript x in p sub x is just a reminder that tells this is the PMF of the random variable x. The argument of the PMF is the specific value that for which p sub x of this value is the probability. Okay, so now if we evaluate this function at a specific small x in the alphabet, this is just a number, is a deterministic value. If we evaluate this function at a random argument big X, this becomes a random variable, and then we take the expectation. So exactly by using this definition applied to this function, we find minus sum over the alphabet, the value of the PMF at the letter small x times the value of the function at small letter x. So you see, it's just the application of the expectation operator to the function minus logarithm of the PMF. Notice one thing. This is very important to remember. Although the notation h of x may hint that this is a function of the random variable x, which would make this thing random because a function of a random variable is a random variable itself, this is not a function of x. Okay? In fact, this expectation, as all expectations, is a number, is a deterministic value, something you can compute and has a specific number. So the symbol h of x is just a symbol, is the entropy of the random variable x is a number. This is very important to remember because otherwise nothing makes sense. Sometimes in information theory we use symbols that have been introduced by Shannon and all the subsequent papers have become, of common use. So it's conventional to use these symbols, and at some point, we start using them without asking too many questions. But at the beginning, it's important that you understand. So to give you an example, we can directly apply this to the case of a binary random variable. So a random variable is called a Bernoulli with probability p. So Bernoulli with probability p means that the probability of x equal to 0 is 1 minus p. Probability of x equal to 1 is p. P is a number from 0 to 1. Or if you want, the probability vector corresponding to this PMF has only two components, 1 minus p and p. Okay? So if I apply this definition, it means summing over the value of the alphabet, so 0 and 1, minus log of the PMF times the corresponding probability. So we have this term for x equal to 1, this term for x equal to 0, they are summed together. This is a function of p. So this, you see, the generic entropy symbol is x, h of x. If I want to indicate a specific binary entropy function as a function of the probability vector, I use this symbol. This is another symbol that is not standard. I have introduced it here for clarity. This says this is the binary entropy function, which is this specific function, and the argument is the parameter p. Because of course, once you specify p, you also specify 1 minus p. So specifying in general p is enough to specify the whole probability vector in the binary case. Okay? So what we can do, for example, is to plot the binary entropy function as a function of p. And as I have anticipated in the introduction, chapter 0, we see that when p is equal to 0.5, so this random variable generates zeros and ones with equal probability, this function is exactly equal to 1. And we see it from here. Why? Because if you compute here, you would have, let's compute it here, the h2 of 1/2 is 1/2 log 2 plus 1/2, because 1 minus 1/2 is also 1/2, log, again, 2, log 2, this is log base 2 of 2 is 1, so this is 1. It's 1 bit. 1 bit of information, which makes perfect sense because, you know, equally probable zeros and ones convey exactly 1 bit of information. So at this point, we can also generalize the definition of entropy to random sequences. So in particular, when I have n sequence xn with a joint probability mass function p sub xn, it's a joint entropy. Is called joint entropy of what? Joint entropy of all the random variables that form the sequence x1, x2, xn. So writing h of xn is the same as h of x1, comma, x2, comma, xn. And the definition is exactly the same, is the expectation of minus logarithm of the joint PMF calculated in the random vector. Explicitly, you get this formula, which is exactly the generalization of the formula we have seen before. Now, what is slightly different, not a direct generalization, is the concept of conditional entropy. So now suppose that we have two jointly distributed random vectors, x, n, and ym. They need not be of the same length, and they need not be defined on the same alphabet. So in general, xn will be defined on alphabet x, ym defined on alphabet y. They are jointly distributed with a given joint PMF, And then we can talk about the conditional entropy of xn given ym. So we have seen the concept of conditional probability and conditional probability mass function. Now we introduce the concept of conditional entropy. So how this is defined? Well, it's simply defined as the expectation of minus logarithm of the conditional probability mass function, minus log of p of xn given ym, calculated in the random argument. And explicitly, this means this formula. Now, at this point, you may say, hey, you made a mistake. There should be a bar here. And I say, no, I didn't make a mistake. There is no bar here. This is really the joint PMF, and this is the conditional PMF. They are different. Why there is no mistake? Well, by definition of expectation. Expectation, when I write expectation of something, this means sum over all possible values of the random argument in the argument of the expectation, and use the joint probability mass function of all these random variables. The expectation is always with respect to the joint probability mass function of all the random objects appearing inside the expectation square brackets. Of course, we can also write this expression in a slightly different way, using the telescopic rule of probability. We can write it in the following way, because if you remember, I can expand this joint probability mass function as p of ym times p of xn given ym and then I can collect in front of this double sum, I can collect this term here that depends only on y, so this can be written, the whole thing can be written as minus sum over y p of y sum over x, and now we have p of x n given y, so xn, sorry, given ym, x, y, log of p, x, n, given y, n, x, given y. Okay? So now you see that we have isolated here a term where the probability outside the logarithm and the probability inside the logarithm are the same, but this term, if I take this term and I circle it in blue like this term itself is dependent on y. This y here and this y here is a particular value of y. And then we need to sum up all these terms that are functions of y, multiply with respect to the probability of y, and then we have the final expectation. Okay? Okay, so this is the conditional entropy. And now we introduce a first important property of the joint entropy, which is very important in the manipulation of these quantities. We'll see later when we deal with quantities as contains random sequences and we want to somehow break them down into simpler terms. This is called the chain rule for entropy. So this lemma says that wait, okay, I have to put the red back, okay. The joint entropy of a random sequence xn can be written as the entropy of the first element, so entropy of x1, plus the conditional entropy of x2 given x1, plus the conditional entropy of x3 given x1, x2, etc., 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 until the last element, which is the entropy of the last element, given all the element before. So in a formula, we can write it in this way, or using the notation that the random sequence from 1 to I minus 1 can be simply written as in this way, as x superscript I minus 1. This is the chain rule, okay? This follows directly from the telescopic property of the PMF, okay? Exercise show lemma proof lemma 1 is like 3-line proofs. It's super easy. From this property and the definition of joint entropy, you get the expansion, okay? But do it as an exercise. It's very important to understand if you are understanding. Some examples. Say we have a random sequence that contains only 2 elements, so we have only element 1 and element 2. Instead of calling them x1, x2, I call them xy, but it would be the same. Then I can expand this joint entropy of x and y in the order xy, and I get the sum of entropy of x plus the conditional entropy of y given x, or in the reverse order. It doesn't matter. You see here we take order 1, 2, 3, 4, 5 until n, but it doesn't matter. We can take any arbitrary order. You would have another expansion of the same joint entropy. So here, if we take the order yx, then we have the entropy of y plus the entropy of x given y. Sometimes one order is much easier than the other. Sometimes, you know, the conditional entropy in one direction is very easy, in the other direction is more complicated. So it is always convenient to find the right order of expansion, as we will see in some examples. Also, we can generalize this chain rule to conditional entropy. So if we have already a conditioning, for example, in this case, we have the joint entropy of x and y given z, so it's a conditional joint entropy, then we can expand with respect to order xy, and we get this, or we can expand with respect to yx, and we get z, this. And it is important to remember that the conditioning here, so this conditioning on z, remains, applies to all the terms, So the common conditioning is always there. Okay. Also to remember is that in general the conditional entropy is non-symmetric, while the joint entropy is always true that the joint entropy of x and y is equal to the joint entropy of y and x, of course, because there is no ordering in the joint PMF, right? It is not true for the conditional entropy. These two terms are generally different. However, it is true that these differences are equal. And this, you can see it simply by this identity, because you can take this term, bring it here, this term, bring it there, and we are going to get this identity. So the difference between the entropy of a random variable x and the conditional entropy of x given y is the same as the difference between the entropy of y minus the entropy of y given x. We will see in a moment that this particular difference takes on a special name. It's called the mutual information, but we are going to introduce the mutual information later on in a slightly different way. I want to introduce another quantity which plays a fundamental role in information theory, but also a fundamental role in statistics. In fact, it has been called in different ways. So in statistics, this is known as Kullback-Leibler distance. In information theory is called typically information divergence, divergence, cross entropy, relative entropy. There are many different names. We are going to refer to this quantity as divergence. So the divergence is defined as follows. We have two PMFs over the same alphabet, P and Q. And the divergence, written as D of P double bar Q, is the sum over all the elements of the alphabet of the probability mass function in first position here times the logarithm of the ratio of the probability mass function in first position divided by the probability mass function in second position. Okay. So this divergence has several important properties. In a certain sense, can be regarded as a sort of measure of distance or how different two probability mass functions on the same alphabet are. In fact, it turns out that first of all, when P and Q are the same probability mass function, then this ratio is 1, log of 1 is 0, the whole thing is 0. So, in fact, we can say, we'll see in a moment, that this implies that P coincides with Q. Okay? It is not exactly a distance because it's not symmetric. So the divergence of P and Q is generally different from divergence between Q and P. We will see in a moment that the divergence, though, is non-negative. So that's a very important property of divergence, that actually from which a whole class of inequalities can be derived, and those are the classical information theory inequalities, also known as Shannon type inequalities. So this is a very fundamental result. And finally, it's important to notice that if for some x in the alphabet, we have that the denominator q is 0 and the numerator p is non-zero, then the divergence is infinite. So in other words, if P puts positive probability on some letters of the alphabet that Q, for which Q is 0, for which they say under the probability distribution Q, these letters cannot appear because their probability of appearance is 0, then the divergence is infinite. That's the case where the two distributions are, fundamentally different, let's say. Okay? So another information theoretic quantity that we will use is the so-called conditional divergence. So conditional divergence is essentially the divergence between two conditional distributions averaged with respect to the conditioning variable. So the symbol is D of P of y given x and Q y given x, and then there is this condition given P sub x, and P sub x is a distribution on the conditioning variable. So this is defined as expectation. And now when you see this, what's inside, that's precisely the divergence between P of y given x and Q of y given x. You see, it has the same structure of this writing. The same structure of this writing, where you have the first distribution appearing in first position, and at the numerator or inside the logarithm, the second distribution appearing in the denominator. So we see here, right? But then those are conditional distributions. So I have marked in red their random conditioning variable. And then, so the whole thing, the whole argument inside the brackets in the expectation operator is a function of x, and x is capital X, is random, so it is a random variable. So outside, we do expectation with respect to x, which means we sum over all possible values of x and multiply by p of x. Okay, so that's the definition of conditional divergence. And when we have two joint PMFs, P of x and y, developed as P of x times P of y given x by the telescopic rule, and Q of x and y, again developed in the telescopic rule, we can use the chain rule for divergence and calculate divergence of the two joint PMFs as the divergence of the two marginal distribution for x plus the conditional divergence of the conditional P of y given x and Q of y given x, where the averaging is with respect to this marginal, which is the one that appears in first position in the divergence. Okay? Good. At this point, I want to introduce the mutual information. Instead of introducing the mutual information as a difference of entropies, this is a consequence, in a certain sense, is another way of writing the same thing, as we will see in a moment. It is more expressive and more meaningful to introduce the mutual information as a special case of divergence. So imagine that we have two random variables, x and y, jointly distributed according to a specific joint PMF, P of x comma y. And now we let P sub x and P sub y be the corresponding marginal distributions. What are the marginal distributions? Well, those are the individual distribution of x and y when we do the marginalization operation. What is the marginalization operation? This is something you have to know because it's basic elementary probability. When I have a joint distribution, if I sum over all the elements of one variable, I get the marginal on the other variable. So the marginal P sub x of x is the sum over all the y's of the joint probability distribution Pxy in xy, and the marginal P sub y is the sum with respect to x of the joint. Okay? This summing over the unwanted variables and is called the marginalization operation, and gives the marginal distribution of the remaining variable, the one that you do not sum over. Now, consider another alternative distribution for x and y, which will be the product of its marginals. In general, the product of the marginals is different from the joint, unless the two random variables are independent, because we have seen last time that by definition of statistical independence, the two random variables are called statistical independent if their joint probability mass function factors in the product of the two marginals. So in general, for statistically dependent random variables, these two alternative distributions, the product of the marginals and the joints, are different. With the special case that when they are independent, they coincide. So basically, the mutual information is defined as the divergence between the joint probability mass function of two random variables and the alternative distribution obtained by the product of the marginals. Okay? So, if the two random variables are effectively independent, what happens? Well, P of x, comma y coincides with P sub x times P sub y, so the two are equal. We said before that when the two distributions are equal, the divergence is 0. So the divergence is 0 for, or the mutual information is 0 for independent random variables. In any other case, when the two distributions do not coincide, well, this mutual information is non-zero, and we will see in a moment it is in fact positive. So in a certain sense, the mutual information is a measure of statistical dependency. The more x and y are statistically dependent, the more different the joint PMF is from the product of its marginals, the larger will be the mutual information. Vice versa, if they are almost independent, the mutual information will be very small. And in fact, in statistics, many times statistical dependency between variables is captured by something called the correlation coefficient. The correlation coefficient is a much weaker notion of statistical dependence. The mutual information, in fact, is perhaps the strongest notion of statistical dependence between random variables, and in fact has a lot of very interesting operational meanings, as we will see along this course, because we will be able to characterize a lot of information theoretic limits for problems like channel coding and data compression in terms of mutual information. So, relation between mutual information and divergence, this is what I have already said, the mutual information is the divergence between the joint distribution and the product of marginals, but there is also an alternative way of writing things, that is through this conditional divergence. And this can be seen basically, well, it can be seen in a moment. Maybe I'm going to do it here. So if I use this definition, if I use this expression, I can write the mutual information as sum over x and y. When I don't write the alphabets, it means that it's over all possible values, and then I have p x comma y x y log p x comma y of x y divided by p x of x p y of y. Now I remember that I can write these joint probability mass function as a p y given x of y given x times px. By the telescopic rule, at this point, I can simplify terms. These and these go away. So I do the same thing here, and what I write is I collect the term for x, px of x, sum with respect to y, py given x, y given x, log y given x, y given x, here is p y. Okay, so now you recognize that these, for every given x, this is a divergence between the conditional PMF of y given x and the unconditional marginal py, and then we have this outer averaging with respect to x, which is exactly the definition of conditional divergence. And it turns out that we can also, well, this is a little bit more difficult, and in fact we will see this maybe as an exercise in a live session. I just say it. One can also express the mutual information in the following way. We take the joint probability mass function of y and x, we expand it according to the telescopic rule, and then we take an arbitrary marginal PMF for y, which need not be py, so the true marginal for y is just any distribution for the alphabet y. And it turns out that after a little algebra, one can show that the mutual information can be written as this conditional divergence, where here we make this new distribution appearing minus the divergence between the true marginal py and this fake marginal qy. So you understand immediately that when we choose qy equal to py, then the second term is 0, and the first term is exactly this term, because qy is equal to py, and then we have this. Otherwise, for any arbitrary choice of qy, we have this difference, and this is very useful to get upper bounds, because as we will see in the next slide, the divergence, I already said it a few times, is non-negative. So if we neglect this term, we get an upper bound. And sometimes it's very useful to upper bound the mutual information, and this upper bound has an interesting point, is that we can choose an arbitrary distribution qy, and so by choosing qy in a convenient way, we can actually obtain computable upper bounds to mutual information that otherwise would be maybe difficult to characterize. So this is a useful tool, is a useful bound that it is used to prove certain results. So anyway, this is, take it as an identity, and maybe in the live session we are going to prove it explicitly, so you see step by step. So those are all ways of writing the mutual information, equivalent ways. So you have equal, 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 and from which you can see that the mutual information is symmetric. So the mutual information of x and y is the same as the mutual information of y and x. It's very easy to get all these expressions. Do it as an exercise. You can start from one and get the others by simply using the usual telescopic rule and simplifying terms. You get everything. Oopsie. Okay. So finally, we get to the mutual information in terms of entropies. So you remember I said these differences of the unconditional entropy minus the conditional entropy is the mutual information, and it doesn't matter in which order we take things, so these two differences are the same. And if you use the chain rule and write the joint entropy as the entropy of one variable plus entropy of the other variable minus the other one, we see here that now we take, for example, in this case, we can take this term, which is this term, write it as the joint entropy minus the entropy of y. With this minus in front, we end up with this, right? Okay, so going on, we can introduce conditional mutual informations. Conditional mutual information of two random variables x and y given z. With this notation, the conditioning is always the bar, so this is the mutual information of x and y given z, is simply the mutual information defined for the conditional distributions, averaged with the expectation is with respect to all random variables. So, in other words, you can say is expectation of logarithm of the ratio of the conditional joint divided by the product of the conditional marginals. And remember, when I have expectation here, it means with respect to all random variables. So with respect to the joint distribution of x, y, and z. And this can also be written as, if we calculate the mutual information for a fixed value of the conditioning variable, so by conditioning on big Z equal to a particular small z, then we have the standard definition of mutual information for that specific value of z, and then the conditional mutual information is simply averaging out over all the value of z this specific mutual information conditional on a specific value of z. Why conditional mutual information is important? Well, for example, because it allows us to find a chain rule for the mutual information. So we will see in many proofs of results that will come, we end up with expressions of this kind, where we have the mutual information between a random sequence xn and a random variable y. And it is convenient to break this mutual information into terms that contains only one random variable at a time. And this expansion is given as follows. The mutual information of xn and y is the mutual information of the first component x1 and y plus the mutual information of the second component and y condition on the first, and then you keep going like this until the end where you have the mutual information of the last component and y condition on all the past random variables. So more briefly, this can be written with the notations that we have already introduced. It can be written in this way. How do we show this? It can be shown directly, again, using a definition of mutual information and using a telescopic property, or we can do it through the entropies. Basically, we write the mutual information of xn and y as the difference between the entropy of xn minus the entropy of xn given y, and then we apply the chain rule to both terms, and then we put things together. Okay, so maybe we are going to do this also as an exercise in the live session. Some inequalities, in particular, in general, for a general case, there is no particular inequality that relates the conditional mutual information of x and y given z and the unconditional mutual information between x and y. In other words, conditioning on z may decrease the mutual information if this conditioning makes the conditional random variables x and y given z more independent, or it may increase the mutual information if by conditioning you increase the statistical dependency. But there are special cases. In particular, there is one case when the joint PMF of x, y, and z factors as the product of marginal x, marginal z, and then y given xz. When we have this special structure, then it turns out that we can prove that conditioning increases the mutual information. On the contrary, special case number 2, when we have another special structure that is called the Markov chain. Markov chain z, x, y. What does it mean, Markov chain z, x, y? It means that if we condition on x, z and y becomes statistically independent. Or, in other words, that the joint PMF factors in this special way as P of z, P of x given z, P of y given x. So in other words, you see when you condition on x, y becomes independent of z because there is no z here in the conditioning. Then it turns out that once we are in this case, then the mutual information of x and y conditioned on z is less than the mutual information of x and y unconditioned. So we have both cases. Okay? Good. So now we are at the point where I would like to prove the non-negativity of divergence. And this follows from a result on convex functions, and in fact, the relation between convex functions and expectation. So I need to define what a convex function is. This may be redundant for some of you, but you know, reviewing concept is always useful. So let's start from the definition of a convex set. So what is a convex set? Consider the real space, real d-dimensional space Rd, and consider a subset, I call it R, calligraphic R, in the real d-dimensional space. We say that this subset is convex if for every x and y in R, the convex combination of x and y is also in R. So what is the convex combination of two vectors? The convex combination of two vectors is basically the segment or the set of all segments joining the two vectors. So if we have, here is the picture, if what I did. Okay, so suppose that, okay, let's add a page here. If I do like this, no, I'm clearly not very smart with this stuff. Add page, yes please, and how can we do this? Paper. Thank you very much. Okay, good. So let's consider the case R2, so D equal to 2. We are in the two-dimensional space, so in the plane. So we have vectors are points. This is a vector. It's a point with coordinates. And if I take two vectors, let's say x and y, and then I consider x times alpha plus y times y minus alpha, where alpha is a number from 0 to 1, basically I describe all the points joining x and y in a straight line. So the segment of the point joining x and y. Because when alpha is equal to 1, we have x. When alpha is equal to 0, we have y, and for any alpha in the middle, we have a point on this segment. Okay, so this is called the convex combination of two vectors. In general, the convex combination of many vectors can be written as, if I have vectors x1, x2, xn, is going to be sum of alpha I xi for the vector alpha, such that all the components are greater or equal than 0, and the sum of the alpha I is equal to 1. Okay? This is the convex combination of those vectors. And now a set, take a set in the plane, right? This is our set R. Is called a convex set if for any 2 points x and y, the segment joining them is also in the set. Okay, so for example, a sort of convex potato like this is convex, but a banana is not convex, right? Because for a banana, I can take this point, and the segment joining the 2 points is not in the set. Is not all in the set. So this is convex, this is non-convex. Okay? And we define the convex hull of a set S as the smallest convex set containing S. We use this symbol, convex hull of S. So for example, the convex hull of the banana would be, let's use a different color, would be, the smallest convex set that contains, so this will be a straight line tangent to the two extremities, and then we have the contour that is effectively convex. So this blue set will be the convex hull of this banana. Okay? And we can also define the convex hull of discrete points. Say, for example, what is the convex hull of these 3 points? Well, the smallest convex set containing these points is the triangle that has these vertices. Okay? This will be the convex hull of these 3 points. Okay?